Okay, and now we will explain how to deal with this curse of dimensionality problem. Okay, so one logical way is we actually need to reduce our feature dimension size, right? And the general idea is, let's say you are given some data with feature dimension big D. So you need to compress your data and their features to a lower dimension and denoted as small d, and your small d should be less than your big D. That means your compressed features will be in a lower dimensional space, So that's the general idea. And there are well established methods in dimensionality reduction. Some are linear, and you may have already heard about principal component analysis or singular value decomposition. But there are some other advanced methods, for example, autoencoders or restricted Boltzmann machines. So these are examples from the neural network community and what we call nonlinear dimensionality reduction techniques. Okay, but in this class we will be mainly focusing on principal component analysis and SVD for now. But when we will be discussing about neural networks, we will be also giving you some background information about these two neural network based techniques. Okay, so to learn the principal component analysis, we need to be little bit clear about the concept of variance. If you are already familiar with variance, then covariance is actually for a pair of variable, for example x and y, and then this is the formula. And just keep it in mind that when we are talking about covariance, we are talking about a symmetric matrix, and we'll see examples in a while. Okay, so here we are showing three scenarios of two-dimensional data points. If you closely look at these data points, the pattern is something like, while x is increasing, y is also increasing. So the direction is something like this if you follow my mouse pointer. Okay, and how that is reflected through the covariance, the diagonal elements are actually the variances of each component. Okay, so x and y. So this is the variance of x, this is the variance of y. Okay, and the covariance value here is 3, and this is a positive value. So positive value represents that their direction is something like both are increasing. Okay, if the value, as in the second case, is negative, then the direction is opposite for x and y. Okay, so here x is increasing but the y is decreasing. Okay, and when you have zero covariance, that means that there is no such directional relationship. It's a kind of random. Okay, so just keep it in mind, these three example cases. Okay, so the idea of principal component analysis is to identify the most varying direction. Okay, and those what we call components. So for example, if you are given these data points, then obviously you can track that this is the most varying direction. So this should be your first principal component. Okay, and as this is a two-dimensional data set, so you will have another perpendicular direction. Okay, because two-dimensional data, you will have two principal components and you want to reduce from 2 to 1, right? So that's your goal or target. Okay, so you have to pick this principal component. But how do we get to this point? So there are some standard techniques that you have to follow. Okay, and we will explain that now. So again, you have a data matrix D, M, and N. You have to apply a standard scalar normalization. So you remove mean and then scale by the standard deviation. And then you have to estimate the covariance matrix. Okay, so your covariance matrix will be of size n times n, as we have seen in our previous example. So the covariance is where 2 by 2 because your data points has two-dimensional features. So you'll get an A n times n covariance matrix. Then what you have to do, you have to solve this linear system. Okay, so A is your covariance matrix, x is an unknown quantity, and lambda is an unknown quantity. We will see through the examples what their size and shape look like, but you have to solve this linear system. Okay, so once you have this system solved, then these x's, we are calling these as your eigenvectors, and these lambda values are scalars, and we will call them as eigenvalues. Okay, x are eigenvectors and lambdas are eigenvalues. Okay, so let's look at some of the example solutions we have provided here. So here you can clearly see that the data is actually the most varying on the y direction. Covariance is 0, and the variances are in the x-axis direction 1, in the y-axis direction 7. So that is reflected through these green and orange vectors, right? And their corresponding eigendecomposition solution are, you have two vectors where we are calling as eigenvectors, and then you have two associated eigenvalues. You can see that 7 is the highest value. So that means that your second eigenvector is actually your more prominent direction that you have to take into consideration as your solution. And how it is reflected through, so you can, if you can track, your y direction is actually your most varying direction. Okay, so the y direction vector is your principal component, and what that tells that if you want to compress, you have to actually project all these data points on this y-axis. No, so that's the general idea of principal component for this particular example. Okay, so if you look at the second example, you see that now the direction changed. Okay, and how we can track it? By looking at their corresponding eigenvalue. Okay, so your solution would be the first eigenvector. Okay, the third and the fourth ones are more interesting because here you can see that you have a combination of two axes. Okay, so you can see that here both the x-axis and the y-axis values are actually changing, and that is reflected through these eigenvectors. Okay, but which eigenvector would you choose for your as your solution? So then you have to track through your eigenvalues, and as you can see that the second eigenvalue is the highest one, so you have to choose the second eigenvector, which is represented through the green vector. Okay, similarly you can explain the fourth case. So if you pay attention, then what's happening, you are actually decomposing your covariance matrix through this linear equation, and then you are tracking that which eigenvalue is the most valuable or maybe with the highest value, and you are choosing the corresponding eigenvector as your solution. Okay, so that's the general idea of principal component analysis. Okay, we'll do some practical problem exploration through notebooks, but this is the general idea. Okay, in terms of optimization, what a PC actually does, so one of the things reduces the variance, a projected space. Okay, so here we have a demonstration. So you have some blue data points. So you can see that the red data points are actually its projections on a single dimension, and if you track, then if you will see that the variance after the projection is the maximum when this rotated axis is actually aligning with this pink line. Okay, so we are saying that if you want to choose the one dimension from your two-dimensional data points, then your projected space would be this pink line, which we call as the most prominent principal component. Okay, thank you. In this part, we will be looking at an example of principal component analysis. So this is a multi-class classification of digits. You guys may have heard about the MNIST dataset. So let's look at the dataset first. And here we'll be doing a 10-fold cross validation. And accuracy would be our metrics. So let's look at some of the data instances. This is an image dataset of 8 by 8 pixels, and this is possibly the example of a 0. We have almost about 1800 records. The images are of size 8 by 8 pixels, so the number of feature dimension would be 8 times 8, that is 64. Okay, and here we are looking at some of the records. So pixel 00, so what is the 00 location value, and then 01 up to 77, so that is of size 64 feature. Let's look at the levels. So the levels are 0, 1, 2 until 9, so we are talking about 10 digits. We are doing a min max scaling, and then we have X is our scaled version of the data, okay? And so we are importing the PCA module, okay? Now what we will do, because our data is actually of 64 dimension, we will compress them 50%. So we will reduce the dimension to 32. So that's what we did here. So we have our PCA instance, and then we are fitting our PCA model, okay? And that actually will compress our data to 32 dimensions. So here, if I pass X to my PCA model and call the transform method, you will have X compressed. You can see that same number of records, but the number of dimensions actually reduced by 50%, okay? So in this figure, we are actually plotting those principal components, that how much variance they were able to capture, and it turned out to be that you actually compressed your data 50%, but it turned out that you only lost less than 4% of your variance, okay? And if you were to just take one component, you would have like captured 15% of the variance. You reduced from 64 to 1, but you were able to capture 15% of the variance of the data. So this is how we read this graph. So first component was able to capture 15%, the second component 13.5, 11.8, and you can see that 32nd component was actually getting less than 1%, okay, of the variance, okay? Here we'll be doing some modeling check, because yes, we were able to reduce our data size to almost half, but how much performance are we losing, okay? Or even in the other way, we might also get some performance improvement, okay? So we'll be testing our SVM model, but you can test with other models. Let's first look with the logistic regression, okay? So we are actually checking that what is the performance of our logistic regression with the original data. So here we have the original data, and now we'll be doing the same with our compressed data, okay? So you can see that the performance actually degraded a little bit in terms of accuracy, 94.15 to 93.87. So you just lost a little accuracy performance, but on the contrary, you see like your actually standard deviation also reduced, okay? So you have a little bit less effective model, but it's a more stable model, okay? How about the SVM, okay? So SVM performance was 97.16 and standard deviation was 0.02. But if you do that with the compressed data, then you see like the performance also improved, 97.66, okay, from 97.16. So you got a little bit improvement, and also your model has less variance, so it's a stable model. So PC actually compress your data, but in most cases it also improves your model performance. Another thing I want to mention here, that let's say your data is at 64 dimension, but you want to project your data for visualization, okay? As humans, we can interpret only up to 3 dimensions, right? So we can compress the data up to 3 dimensions or 2 dimensions and plot our data for visualization purposes, okay? You compress your data to 2 dimensions. So you see like the same number of records, but you only compress to 2 dimensions, and then you are plotting your data, okay? So now see, because we have 10 classes 0 to 9, and you can see some of the items like 0 are separated even in the 2-dimensional space. But some of the items like 9 and 3, some people actually write 3 in a way it looks to be 9, because they have similar kind of curvature, right? So that's why you see like here we have 3 and 9 kind of a little bit overlap. But anyway, this is not the actual data. We are just for visualization purposes, we are looking at the data in a 2-dimensional space, but first using PCA to project them into a lower dimension, okay? So PCA is a linear dimensionality reduction technique, and this notebooks actually explains that how to use PCA, given that we are using the scikit-learn implementation of the PCA, okay? Thank you.